Okay, this time around we're going to take a look at equations that have radicals in them and how to solve them. Basic ones. We won't get into anything too complicated here. So, what is a radical equation? What kind of equations are we actually going to take a look at solving? So, we're going to look at equations that contain a radical that has a variable in its radicand. So not only are we going to have a radical, but that radical will have a variable uh, underneath the radical sign, so in the radicand. So to solve these kinds of equations, we're just going to do three basic things. We're going to isolate one of the radicals, if there happens to be more than one. We're going to isolate one of the radicals containing a variable. Then we're going to use our property that says if you take the nth root of something and raise it to the nth power, the radical sign disappears and you're left with just the radicand. And then we're going to solve the equation that's left. So those are three general steps that we're going to follow to solve radical equations. So let's give it a try. So this is a radical equation because I have a square root, which is a radical, and there's a variable x in the radicand. So to solve this, we want to get the radical by itself. Well, the first one we have here, the radical is by itself. So we have the square root on the left side of the equation all by itself. So it is isolated, which was the first step that we discussed. The next step is that we want to take this square root and we want to raise it to the second power to make the radical go away. So if you go back and look, that was one of our properties at the beginning of our study of radicals, is if you have the nth root of something, if you raise it to the nth power, the radical sign goes away and you're just left with the radicand. So we're going to use that property right now. So the very first step is we're going to take the square root on the left side and we're going to square it. Now mathematically, it's not legal to just square the left side of the equation. The only way it's legal is if you square the right side of the equation. So you have to do the same thing to both sides of the equation. Alright, so when you square a square root, in this case we're left with just the radicand, and 3 squared is 9. We'll add 1 to the other side and get 10. Divide both sides by 2 and we'll get 5. So we see that the solution to this equation is x equals 5. But remember, we write our answers as sets. This is algebra. We use set notation. So it'd be the set of all x such that x is 5. To check this equation, you check it the same way you check any equation. You take your answer and plug it in and see if you get a true statement. So 2 times 5 is 10, minus 1 is 9, the square root of 9. The principal square root of 9 is 3, which is what we have, so that's true. Let's solve, then check this one. So on this one, I have a cube root with a variable in the radicand, but it's not isolated. It's not by itself. I've got this -1 here, and I've got this +2 I got to deal with. So first thing we're going to do is add 1 to both sides. And then I'm going to divide both sides by 2. So now the cube root is isolated. So since it's a cube root, I'm going to raise both sides to the third power. So whatever the index is, that's the power you raise it to. That's what the property says. That's what will allow our radical to disappear. So the cube root of x, when I cube it, I'm going to end up with x, and then 2 cubed is 8. So my solution is the set of all x such that x is 8. Now on this one, let's take a second and make sure we understand why raising it to the third power works. Okay, so on this step right here, we raise both sides to the third power, and all of a sudden the radical disappears. So why is that true? Well, let's see. When I raise something to the third power, I'm multiplying it by itself 3 times. So that would that would be the cube root of x times the cube root of x times the cube root of x, and on the other side that'd be 8. And the cube root times the cube root times the cube root, as we already know, is a cube root. X times x times x is x cubed. And this property we've been using for quite a while now. The cube root of x cubed, x gets to come out of the radical sign. So rather than do that, which is a lot of writing, we just use, it's basically a shortcut, but it's a property that just says when you raise it to the same power as the index, the radical sign disappears. And this is up here in blue is why it works in this particular one. And it's the same idea when you do this anytime. Anytime you raise an nth root to the nth power, this basic idea is why the radical sign goes away. Okay, let's check our answer. So we have 8. Let's plug it in and see what happens. So 2 times the cube root of 8 minus 1 equals 3. Cube root of 8 is 2. 4 minus 1 is 3. That's true. So 8 is the solution to that equation. All right. Those are some pretty easy ones. Let's look at a little bit more complicated ones. So this next equation, we have 3x minus 5 times the square root of x equals 2. So as you can see, we have a radical with a variable in the radicand, and we need to isolate that. So let's move the 3x to the other side. Now, I can divide both sides by -5. That's perfectly okay. And if I do that, I'm going to get -2/5 plus 3/5 x. Now, there's nothing wrong with that, but the next step is going to be to square both sides. So I'm going to end up having to square that, and it's got fractions in it, which can be kind of a pain. So even though we could do that, it might actually be a little bit easier for us if we don't divide by -5. Instead, what if we just square both sides as it sits? Let's see if that'll work. So if I square this, -5 squared is 25, and then the square root of x squared would be just x. So the radical disappeared, and on the right-hand side, we have 2 minus 3x times 2 minus 3x. So we got rid of the radical, and we don't have to deal with any fractions. So in this case, leaving that -5 out front is probably going to end up being a little easier. All right, so let's multiply those two binomials together. So we'll get 4 minus 6x plus 9x squared. And then let's move everything to one side. So I'm going to have 9x squared, and then I'll have -12x. But I'm going to move this 25 over to the right-hand side. So minus 25x, and then we'll have plus 4. So we'll have 0 equals 9x squared minus 37x plus 4. All right. So let's see if we can factor that. So that would be, let's try 9x and x. And then let's try 1 and 4. Because that would give me 36 and 1, which gives me 37. So that should work. And if they're both negative, I'll get a plus 4 and a -37. So 9x minus 1 equals 0, or x minus 4 equals 0. So x equals 1/9, or x equals 4. So it looks like we have two answers. So now let's check our answers. All right, let's check that first one, 1/9. So we'd have 3 times a ninth minus 5 times the square root of a ninth equals 2. So that would be 1/3 minus 5 times, well, the principal square root of 1/9 is 1/3. equals 2. So 1/3 minus 5/3, that does not equal 2. That's a false statement. So that actually is not a solution. So what about 4? Maybe 4 is. So 3 times 4 minus 5 times square root of 4 equals 2. So that'd be 12 minus 10, which is 2. That's true. So x equals 4 is the solution. So it's the set of all x such that x equals 4. But that's it. The other one does not work. 1/9 did not solve that. So anytime you solve one of these and you get an answer that doesn't work and an answer that does, the one that doesn't work is called an extraneous solution. So x equals 1/9 is an extraneous solution. What that means, if you look at the first 5 letters, is extra. It means it's not needed. It's an answer that we got when we're solving, but it's actually not needed. We toss it aside because it does not solve the original equation. It doesn't solve the original equation. So we toss it aside. So the only answer is 4. Now that doesn't always happen, by the way, but so you just got to check all the answers you get and see which ones work and which ones don't work. Let's try another one. So now we've got the square root of 5 here. Now the reason I put this one in here is to show you that just because there's a radical in the equation doesn't mean we have to use that it's going to be a radical equation and we have to do all this fancy stuff to solve it. If you look closely, I just have square root of 5. That's just a number. There's nothing fancy about square root of 5. It's just a number. So this equation right here is not a radical equation and doesn't require anything fancy to solve it. We just solve it like we solve any linear equation. So we could have done this equation at the beginning of the year. So to solve this, we're just going to combine like terms. So I'm just going to take 3x. I'm going to subtract x times the square root of 5 from both sides. I'm going to factor out my x. And then I'm going to divide both sides by 3 minus the square root of 5. Now technically that's the answer. However, the answer is not simplified. We have a square root in the denominator, so we need to simplify that answer. So we're going to multiply the top and bottom by the conjugate to simplify that answer. So we'll get 2 times 3 plus square root of 5. On the bottom, we'll get 9 plus 3 square root of 5 minus 3 square root of 5 minus the square root of 5 squared. So we get 2 times 3 plus the square root of 5. And then on the bottom, we're going to get 9 minus 5, which is 4. And 2/4 will simplify. So x equals 3 plus the square root of 5 all over 2. So that's what we think the answer is. So it'd be the set of all x such that x equals 3 plus the square root of 5 over 2. But we should always check our answer. So let's see what happens when we check. So we're just going to plug this answer in for x. So it'd be 3 times what we think the answer is equals 2 plus what we think the answer is times the square root of 5. Well, let's look at the right-hand side. The right-hand side, I have a fraction, so I need to get a common denominator. So this would be 4 halves plus square root of 5 times 3. Square root of 5 gives me 5 over 2. So I'm going to get 4 plus 5, which is 9, 3 square root of 5, all over 2. Well, look what I have. I have 9, 3 square root of 5 over 2. So it does check out. So that is the correct answer.